We'll be continuing on with the topic of intermolecular forces in this next section on solutions. Primarily, we'll be talking about aqueous solutions, as water is our primary solvent and biological solvent. But it's also important to remember it's not just how polar and ionic compounds dissolve into, but part of the phenomena that's so important about water is the way that nonpolar solutes organize themselves away from water. So we'll be talking about this a little bit more and how important it is in biological systems. Here are a couple of examples of vitamins, vitamin C and vitamin A. In general, vitamins are compounds needed to build important biological cofactors. A couple of examples of these would be NAD, FAD, and acetyl-CoA, which are important for all of the metabolic pathways in biological systems. Vitamins can be categorized as either water-soluble or fat-soluble. If we look at the features of a water-soluble compound, in general, when we're talking about water solubility and organic molecules, let me say organic means that they are carbon-based. And you can see all of the carbon, just to kind of underline here, all of the different carbon in these molecules. I don't have to underline them all, you can get the idea. Hydrocarbon being hydrogen and carbon. You can see the difference between the two molecules if we look at them. But in general, water-soluble vitamins are going to be less than 6 carbon and have oxygen, nitrogen, OH, NH, substituents throughout the molecule. Fat-soluble are going to be hydrocarbon-based. So I'll just write carbon and hydrogen here. So let's go back and look at vitamin C. And this is something that you know we get from citrus. And also things that are acidic, green bell peppers, jalapeno peppers, and then of course all of the citrus fruits. We'll just put a circle all of the different oxygen here in this molecule. And you can see that there are both B dot dot, or oxygen with lone pairs. Remember, we don't always see them, but they're there. If there are 2 covalent bonds in this type of bonding pattern, oxygen will also have 2 lone pairs to complete its octet. So we have B dot dot and AH groups throughout the molecule, which means that water can get in here all around the oxygen and make hydrogen bonds. Okay, so that's what is needed in order for a substance to dissolve in water. It has to be able to allow the water in and around it in order to solvate it and make a solution. Then if we look at vitamin A on the right-hand side, which is fat-soluble, you can see that there is no oxygen, there is one oxygen, right there. But there's only one, and we've got a bunch of different carbon in this particular molecule. That's not enough for this compound to be water soluble because the water cannot penetrate in these areas. The carbon and the hydrogen, because they are nonpolar, will repel water away from them. So it becomes important in our biological system how we digest and consume these foods, in what order, how the vitamins are uptaken. So something that is fat soluble or lipid soluble, you need to eat some healthy fat in order to be able to get these vitamins to be digested and metabolized. As I said previously, we'll be talking about water as the primary solvent, but we also have something called organic solvents, which I'll talk about more in just a moment. Let's go ahead and define our three basic terms here: solution, solute, and solvent. A solution is at least a two-component homogeneous mixture. The second term, solute, is the lesser component. Another way to say that is whichever one I have less of. Lesser component in the solution. And the solvent is the greater component. In the solution. It also typically defines the phase of solution. All right, here we have an example. We have water as our solvent, and our solute is sodium chloride. And what happens there is remember we've got water's Lewis structure looks like this. And so in the middle part, we've got a little bit of a negative charge. And on the ends, we have a little bit of positive. And so our ions, the water will pull them apart. Well, let me just make those different colors so you can see that a little bit better. And once it pulls the crystals apart, then it dissolves the salt. And that salt is dissolved because it still retains its properties. It will taste salty, and you probably don't want to drink salt water. An organic solvent, the other type of system, not water-based. So it means that these organic solvents will be good for non-polar molecules. Again, organic, that term in chemistry means carbon-based or carbon and hydrogen-based. A common misconception is that solutions are only equal to solids plus liquids. But here is a chart that shows some different types of solutions. So it's possible to have a gas-gas solution, and then all different types here: gas liquid, liquid liquid, solid liquid, and even rarely solid solutions. Okay, looking at the examples, a gas solution would be air. Air is not pure oxygen. The major component is nitrogen. In fact, nitrogen is around 78% by mass of air, and oxygen, I can't remember off the top of my head, it may be 14%, somewhere in that ballpark. And oxygen, as you know, is flammable, so we would not want 100% oxygen all the time, or any spark could possibly be hazardous. Gas liquid solutions, any type of soda is going to be true, and we like, or at least I do, when carbon dioxide content is high, because it makes it fizzier, which is a technical scientific term, but it also lowers the pH. producing something called carbonic acid. When we mix CO2 plus water, just literally H2O plus CO2 is this compound here, carbonic acid. And that phenomena also becomes important when we talk about things like acidosis and proper blood pH. It's possible to have a liquid-liquid mixture, drinking alcohol, rubbing alcohol, or a couple of common mixtures. Vinegar is also kind of in the same family. Solid liquid, again, this is our most common type of solution, something like salt water. And then you can also get alloys, brass, and the I guess the amalgam that they use for dental fillings is technically a liquid solid mixture, but they're much more rare, but they are possible. The degree of solubility is going to depend on nature and composition of a solute and the way it interacts with the solvent. Or another way to say that is the intermolecular forces that are between them. But we also have to consider something else called entropy. It's not something we've talked much about yet, but will more when we get to thermodynamics. It's abbreviated as S, and a lot of times you see the reference of delta S or the change in S. But this is defined as the degree of order in a system. And has to do with the second and third law of thermodynamics. So we'll get to more of that later. All right, looking at this example here, we have two pure substances, neon and argon, and there is a barrier between them. Okay, so we've got two pure substances. That barrier is removed, and the two pure substances now make a solution. Why do they do that? Well, they're in the gas phase. These are noble gases, and so they're going to be moving around, bouncing off the walls of the container. And then when we put them together, they're going to bounce off of each other, bounce off the wall, and it's going to spontaneously mix. It's kind of what we saw with our food color and water. So entropy tells us that it is favorable for pure substances to mix and become solutions. In other words, it becomes less ordered, more random. So if there is a significant amount, if there are intermolecular forces between two substances, they're similar, they are going to mix spontaneously. Remember, when we're talking about intermolecular forces, just a quick reminder that all molecules have dispersion forces. But the presence of polar groups, dipoles, hydrogen bonds, or ionic charges themselves, things that are positive and negative, are going to promote solubility in water. So that means that our organic solvents are going to work best for things that have hydrocarbon only, are big, and not soluble in water. An important thing to remember also is when we start looking at biological molecules, you have things like phospholipids, that are amphipathic. Let me change colors here and write that term, amphipathic, which means that they have dual natures. And we look at the root word there. The amphibian is another word where we see that particular root. It means that it has a dual nature. And so there's going to be a water-soluble end and a nonpolar end, which allows for things like cell membrane formation. So that's important in biological systems. If everything was water-soluble, it couldn't organize into discrete cells. And you might see a cell phospholipid being abbreviated sort of like this. What that represents is the two ends of the molecule, the polar part shown there, and the nonpolar. Here's a chart that we'll refer to several times when we work problems, table 12.3, which shows polar solvents and nonpolar solvents. So we could just divide down them. This would include the polar solvents are going to be solutes that have dipoles, can make hydrogen bonds, or are ionic substances. Nonpolar solvents are going to work well for organic molecules that are big and have carbon hydrogen only. So we look at some examples here. You'll see, water makes hydrogen bonds, but you also see the polar groups here. And in the case of methanol and ethanol, they can make hydrogen bonds as well. Now, if we look over at the nonpolar solvents, you do see something like carbon tetrachloride. And chlorine is an electronegative molecule, but remember that those polar groups will cancel out if carbon is attached to only chlorine. That is, there are not other atoms that are bonded to that central carbon. And in the case of diethyl ether, there is a polar oxygen there, but the more carbon you get around it, the less water soluble it is. So we have some things that are relatively polar as compared to hexane or toluene, and you can see here that this is only carbon and hydrogen. So we would call hexane a dry solvent because it does not have any water, it doesn't have any polar groups. So remember this chart and we're going to refer back to it. Let's look at a couple of example problems related to solutions. Pick an appropriate solvent from the table. Remember we had our polar and nonpolar to dissolve each substance. State the kind of intermolecular forces that occur between the solute and solvent in each case. So number one here, example is motor oil. If you know anything about oil and water, we know that they are not miscible is the chemical word for that. So it is not, I'll put water and then I'll put a red X through it, not water soluble. So we want something like hexane or toluene to be a good solvent for that. And the only type of intermolecular forces between them will be dispersion because these are carbon and hydrogen only. Right, second example, ethanol. And ethanol was on the list of polar solvents because it can make hydrogen bonds. Water would be a good solvent for it, and we know that ethanol and water mix well. Any on that list, though, would work. The acetone or the methanol would also be a good solvent. Number 3, lard. And this is solid fat. So again, think, the fat that is on your steak. It is not water soluble. So I'll just write that again with the X through it. Not water soluble, so Dispersion forces only, hexane or toluene would do better than the dimethyl ether or the carbon tetrachloride. And our last example, potassium chloride, KCl. Anytime I see a IDE ending, that is a dead giveaway that it is a compound. This is ionic. Anything that has a metal ion will be an ionic substance. So again, that's going to be an ion dipole. Water is going to be a very good solvent for that. This is a different type of example problem. In this case, I'm showing the structure. So again, I want to think about the type of intermolecular forces. We're going back to that same chart there, polar versus nonpolar. Right, so my first compound here, it's a sugar. And remember, we haven't shown that as much in this particular section, but each point represents a carbon. So I have 1, 2, 3, 4, 5, 6 carbon. But I also have a lot of oxygen and hydrogen here. So that tells me that this would be water soluble. It can make hydrogen bonds with water. It would have solubility in ethanol and methanol as well. But water's the best solvent. All right, let's look at the second example, number 2. Here, again, each point represents a carbon, and there are hydrogen attached to it. Okay, but there is no oxygen or nitrogen on this particular molecule. It is carbon-based. And so my best solvents would be hexane and toluene. And the type of intermolecular force is dispersion only. Right, number 3. These points right here represent 2 carbon atoms. It does have 1 oxygen, but it can't make hydrogen bonds. It would have some solubility. This one is kind of tricky because it is something that could interact with some of the polar solvents and also a couple of the non-polar solvents. So water would be okay. Acetone would be really good with this particular compound. It looks the most like acetone. Ethanol and methanol would work as well. But your diethyl ether, which is the one that's got the oxygen in the middle, it's got 2 carbon and an oxygen and then 2 more carbon from that chart without drawing it all. It looks a lot like this particular compound. And so it would have solubility in that as well. So that one's a little bit tricky. All right, the fourth example here. This one is an amino acid. It is in particular alanine, although that doesn't matter for our purposes. We look at the number of carbon. There are 1, 2, 3, and then I have 3 oxygen, nitrogen type things around it. So this one is water soluble because it is dipole and can make hydrogen bonds with water. All right, so there's a couple of example problems. It's also important for you to know the definitions of solute, solvent, and solution, the 2 different types of solvent systems, whether we're talking about something that is polar or nonpolar.